So in the previous lecture, we completed our discussion on one-point compactification of a non-compact, locally compact, non-compact and locally compact topological space. So we also discussed the quotient topology, and in the exercises this will be used to prove that to prove that various examples of topological groups that we saw are connected. Now, let me write as to prove connectedness of various topological groups. We saw. So in this lecture, we will show that there is a large class of topological spaces which possess many continuous functions. That is, continuous maps from X to R. So let's say we are talking about continuous real valued functions. So the meaning of many will be clarified later. Okay. So, but before that, we need to define something. So recall that a Hausdorff space is one in which open sets separate points. So what this means is that given any 2 points, there are 2 disjoint open sets such that, so given 2 points x and y, there are 2 disjoint open sets u and v, so that x is in u and y is in v. So we can generalize this and ask for a stronger condition. normal, a normal topological space. So X is said to be normal if for any two disjoint closed subsets A and B, there are disjoint open subsets U and V such that A is contained in U and B is contained in V. So this could be A and this could be B, let's say in R2, and we could just take two open subsets containing this. So the first useful property that a normal topological space has, which we will need, is the following. Well, before that, maybe we can see an example. So proposition. So this proposition shows that there are many normal topological spaces. Every metric space is normal. Proof. So let X be a metric space. And let A and B be closed subsets of X. So recall the distance functions. The functions t sub A from X to R and t sub B from X to R. These are distance functions from A and B. So for each, so let's make a picture. So let's say this is my A and this is my B. So for each A in A, let epsilon A, this is the distance of A from B divided by 4. And similarly, let for each B in B, let epsilon B be the distance from A of B divided by 4. So we define open sets. U to be union A in A, the open ball around A of radius epsilon A. So in this, for instance here, the distance between is probably going to be this length, because this seems to be the closest point to A. And then when epsilon A is going to be, this B A epsilon A is going to be this ball. And we take the union of such balls. And this open subset B to be equal to union P in B, P. So then clearly A is contained in U and B is contained in. So we claim that U intersection V is empty. If not, there or if not, then there then there are A in A and B in B such that B A epsilon A intersection B B epsilon B is not empty. So let's pick an element y in this intersection. So what this means is that, so use as X is a metric space, so we get that dA comma B is less than equal to dA comma Y plus dy comma B. This is less than equal to, so since y is in BA epsilon A, this is less than equal to epsilon A plus, and since y is in B comma epsilon B, this is less than equal to epsilon. So we may assume epsilon A is less than equal to epsilon B. So then this will be less than equal to 2 times epsilon B. But on the other hand, uh, this dA comma B is greater than or equal to the distance of B from A. Distance of B from the set A. So this means that we will get 2 epsilon B is equal to d AB by 2. However, as A and B are disjoint, or as A is closed, DAB is equal to 0 if and only if B belongs to A, which is not possible as B belongs to B and A and B are disjoint. Thus, DAB is positive, and so this is which gives a, so therefore this we get a contradiction. So this completes the proof of the proposition. So this shows that there are lots of normal topological spaces. So next, let us prove a useful lemma. So let X be a normal and let A be a closed subset. So let W be an open subset such that A is contained in W. Then there is an open subset V such that A is contained in B, which is contained in B closure, is contained in W. So let us prove this. So the set, so if we were to make a picture, so A could be this A, and our W could be the complement. Well, a W could be this open subset. So what we do is the sets A and X minus W are disjoint closed subsets. So thus there are disjoint open sets V and U such that A is contained in V. So V could be something like this, and X minus W is contained in U. So in particular, so it is an easy check that V closure intersected X minus W is empty, which implies that V closure is contained in W. So thus A is contained in V, is contained in V closure is contained. So this proves the lemma. So proposition. So what do we mean by a continuous function that separates two sets? So let X be a metric space. So this proposition will, in this proposition, we will see a simple example of, and let A and B be disjoint closed subsets. So then there is a continuous function f from x to 0, 1 such that f of a is equal to 0 and f of b is equal to 1. So for metric spaces, the proof is very easy. So take f of x to be equal to dAx divided by dAx plus dBx. So note that the denominator never vanishes. Never vanishes. As A and B are disjoint and closed. So in particular, so this shows that f is continuous, and it is easy to check that f has the required properties. So what we want to do next is that we want to prove the same result for normal spaces. So this is a very famous theorem. Which is called Uleson's lemma. So let X be a normal topological space. and let A and B be disjoint closed subsets. Then there is a continuous function f from x to 0, 1 such that f of a is equal to 0 and f of b. So maybe first we can see the motivation behind the proof. That might help a bit. So before we begin the proof, so let us assume that suppose we have such a continuous function. F from x to 0, 1 such that f of a is equal to 0 and f of b is equal to 1. So then for each q in this open interval 0, 1 intersected rational numbers. So we are taking a rational number which is greater than or equal to 0 and strictly less than 1. So we get the set which we call uq is f inverse of 0 comma q. So this is open in X, which is open in X and contained in X minus B. So notice that if Q1 strictly less than Q2 and both are in intersected Q, then UQ1 is contained in UQ2. And also notice that f of UQ1 closure is contained in f of UQ1 closure, which is contained in 0 comma Q1. Thus, UQ1 closure is contained in UQ2. Sorry. So first we should write UQ1 is obviously contained in UQ1 closure, and this is going to be contained in UQ2. So motivate. So if there is a continuous function f, then we can find open subsets indexed by rational numbers which have this property that every time q1 is strictly less than q2 and both of them are in 0, 1 intersected q, there is a ordering like this. So motivated by this, to prove the theorem, we shall find such a sequence of open sets on X and try to define f using the sequence. So now we begin the proof. of Ulison's lemma. So since A and B are disjoint closed subsets, this implies that A is contained in X minus B, and we define X minus B to be this open subset U1. So using the using the lemma we proved above, we can find U naught such that open such that A is contained in U naught, is contained in U naught closure, is contained in U1. So now we want to find our sequence of open sets. So step 1. So let Q be a rational number. Well, first, as Q intersection 0, 1 is countable, we may index its elements using the set. So that is, we write Q intersection 0, 1 as Qi's I greater than equal to 0. So further, we may assume that Q0, well, let's say by natural numbers. Q1 is equal to 0 and Q2 is equal to 1. So now, so we have defined UQ1, which is U0, and UQ2, which is U1. So inductively, we will define UQs, well, UQJ for each j greater than equal to 3. So assume we have defined UQI for Qi in this set, Q1, Q2 up to QR. So so then we need to define UQR plus 1. So this is Q1, this is Q2, and let's say Q3 is here, Q4, Q5, Q6, and so on. So the point is there is a unique, or not a unique, there are unique okay, I comma j such that qr plus 1 is strictly is contained in the interval qi and qj. So the already existing QIs, they partition the interval 0, 1 into various pieces, and the QR plus 1 is going to be contained in exactly one of these pieces. So for instance, QR plus 1 could be here. So we take UQR plus 1 to be an open subset satisfying UQI closure is contained in UQR plus 1 UQJ. So we are applying the lemma to the open subset, to the closed subset A, and to this set W. And we can find UQR plus 1, any open subset which satisfies this condition. So proceeding in this way, we would have found open sets UA for each rational number A which is in the interval 0, 1, such that they satisfy UA closure is contained in UB if A is strictly less than B. So step 2, for P strictly less than 0, define UP is the empty set, and for P strictly greater than 1, define UP is the whole set X. So once again, so now we have defined for each Q, for each rational number, so let me use this A, an open set, use of A which have the property that A strictly less than B implies UA closure is contained in U. So we have defined our sequence of open sets. So in step 3, we will define our function. So given X in X, denote by S sub X the set of rational numbers P in Q such that X belongs to UP. So note that if P belongs to Sx, then every rational number Q such that Q is greater than or equal to P is also in Sx. So we define a map f from x to r by setting f of x infimum p in s sub x. So s of x is like alpha comma infinity or alpha comma infinity intersected with q. Well, uh, for some real number alpha. So this follows easily from this remark. So we need to check the following. One, f of x lies in the interval 0, 1. 2, f of a is equal to 0. 3, f of b is equal to 1. And finally 4, f is continuous. So let us check 1. So let x in x be any point. So if a belongs to q and a is strictly less than 0, then u sub a is the empty set. So this implies that a does not belong to S of x. So that means that no point which is strictly less than 0 is in S of x. So this clearly implies that f of x, which is infimum of the elements of S of x, well, okay, so is going to be greater than or equal to 0. Similarly, if a is in q and a is strictly greater than 1, so this implies that a u sub a is all of x, which implies that a does belong to S of x. So that is S of x is contained in 1 comma infinity intersected with q. So this clearly implies that f of x, which is infimum of S sub x, is less than or equal to 1. Oh, I'm sorry, I want to write the other way. This means that every rational number which is strictly greater than 1 is contained in S of x. Right. So this implies that f of x, this proves 1, is contained in the interval 0, 1. Because we have proved that for each x, f of x is greater than or equal to 0, and it's also less than or equal to 1. Okay, so let's prove the second property. If x belongs to A, then x belongs to U0, which implies that 0 belongs to S sub x, which implies that f of x is less than or equal to 0. But as we already showed that f of x is greater than or equal to 0, this implies f of x is equal to 0. So this proves so 3, let us prove that f of b is 1. So if x belongs to b, we claim that S sub x is contained in 1 infinity intersected with rational numbers. If this is not true, then there is p less than or equal to 1 and p in q such that p belongs to S sub x. P cannot be equal to 1 as x does not belong to u1, as u1 is equal to x minus p. Thus, p has to be strictly less than 1. But then, as we observed, but if p is strictly less than 1 and p is in S of x, then 1 belongs to S of x, which is a contradiction. So this shows that S sub x is contained in 1 infinity intersected with q. So this implies that f of x is greater than or equal to 1. Yeah. But as f of x, which is infimum, let me just remind, is greater than or equal to 1. But as is less than or equal to 1, this implies f of x is equal to 1. And finally, we want to prove that f is continuous. Finally, we will show that f is continuous. So it suffices to show that for any two rationals, C strictly less than D, the set F inverse CD is open. So suppose X belongs to F inverse C comma D, then choose rational numbers P and Q such that C is strictly less than P So we will show that A x belongs to uq and this is contained in F inverse of C comma D. So let me write this as P. And B. So as f of x, this is infimum of s sub x. This is strictly less than q. So this implies that there is some rational number q1 inside s of x such that q1 is strictly less than q. So this implies that x belongs to uq1 and uq1 is contained in uq. So this implies that x belongs to uq. So similarly, as p is strictly less than f of x, so this is infimum of s sub x, this implies there is p1 such that p is strictly less than p1 and p1 does not belong to s sub x. Thus, x does not belong to up1 and up is contained in up closure is contained in up1. So this shows that x belongs to uq minus up closure. This proves A. Note that this set is open. This set is open in X. So now we prove B. So next, let us show that UQ minus UP closure is contained in F inverse CD. So if Y belongs to UQ, this implies that Q belongs to S sub Y. This implies that F of Y, which is infimum over the elements of S sub Y, is less than or equal to Q. And as Y does not belong to UP closure, this implies Y does not belong to UP. This implies P does not belong to S sub Y. So this implies that f of y is greater than or equal to P. Because remember that S sub y is some interval like this intersected with rationals. And P does not belong to S sub y. So P has to be somewhere over here. So the infimum f sub y, which is the infimum, has to be greater than or equal to P. So thus, f of y is in this closed interval P comma Q, which is contained in this open interval C comma D. So this implies that UQ minus UP closure is contained in F inverse C comma D. So this proves that f inverse c comma d is open, which proves that f is continuous. So this completes the proof of the theorem. So as a corollary, which is the moral of Uleson's lemma, is on a normal topological space, continuous functions can separate disjoint closed subsets. So in this sense, there are many continuous functions. So we will end this lecture here.